All right. Hey, everybody. I'm Stephen Bates. I'm talking today on behalf of the Toronto Emerging Storage Lab, of which I am the director. This is a Huawei research group based in Toronto and hopefully eventually across Canada. And the work that we're going to talk about today is kind of some groundwork for emulation, not just of computational storage stuff, but other things. I think there's some really cool things going on around hardware emulation that is really, really useful for people who are developing storage software. So I kind of want to touch on that quite a bit today. So the title of the talk is an emulation framework for computational storage, but really I'm going to talk about hardware emulation in general. I absolutely love emulation. And I always think of that movie Inception, which I'm sure many of you have seen when I think about emulation, because one of the things that, I always imagine is that you're in a world where you have no way of knowing if the things that you're talking to and interacting with are actually real, in the sense, are they real hardware? Or are they emulated constructs that are presented to you through something like a hypervisor or a virtual machine manager? So in the same way that the characters in Inception don't really know if they're in a dream or not, and some of them use totems to work out whether they are, we can do something similar. And it's interesting, in NVMe, in the technical working group right now, this is public domain, so I can talk about it. We're talking about live migration of NVMe controllers and subsystems between virtual machines. And in the same way, those VMs, when you do a live migration, should not know or care that migration is happening. So this presents us with a lot of opportunity. So is it real or is it emulated? Is the hardware you're talking to in your system as a software developer real or is it emulated? And do you even care? And I think one of the things I want to try and convey today is that in a lot of cases, unless you're doing performance testing, you probably don't care whether you're talking to real hardware or emulated hardware. You can still get your work done just the same. And there's a lot of advantages to emulated hardware, and we'll talk about them a little bit in this talk. Okay, so the case for emulation. Hardware is hard. I've spent a reasonable amount of my career working on low-level chip design for storage. We did, early PCIe-based SSD controllers and sold them to hyperscalers and storage OEMs who then built SSDs out of them. And building that kind of silicon is really, 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 really hard, right? And I'm sure there's some of you in the room who've also worked on complicated silicon, and it's really hard. It's really expensive, and it's getting more expensive, right? Taping out a chip is a ridiculous amount of money. And it takes a lot of time, right? A chip design from start to finish is measured in years, right? Not months, not weeks. And the problem, of course, is if this is a chip that, for example, is going into a bigger system and it has to talk to a main processor and it needs a driver, you can't start writing those drivers and the software that might live above those drivers until you have real hardware, unless you look at something like emulation. So there's a lot of challenges with real hardware. It's just really freaking hard. Okay, so the case for emulation, part one. Hardware is hard. Chips take a long time to develop, right? Chips today need firmware, right? So, when a while ago, it was probably a little more unusual to have a chip that required firmware to run, but nowadays, firmware blobs literally have to get loaded into tens, if not hundreds, of little MCUs and processors on your chip. That firmware can be buggy as well. And chips are often, I would almost say always, broken first time around. We typically, when I worked in the chip business, assumed a second tape out, at least metal layer fixes. And sometimes it was a lot more than just metal layers, right? Look at CXL, for example. I think CXL is great. Well, the spec is at, 17.0? No, It's at like 3.0, maybe 3.1, maybe someone can correct me. I would say the hardware right now is at less than 1.0 in the sense that, have you tried to bring up a CXL connection anytime recently? I have, and it's pretty damn hard. All right. So what do you do if you're a software developer? What if you want to write a Linux driver for a CXL device? What if you want to write a Linux driver for an NVMe device that supports a new command set? Like, what do you do? All right. How do software developers develop without hardware? Other emulation tools exist. You can write your own, you can do other things, but I'm going to focus today on QEMU. I love QEMU for a variety of different reasons. And also it's a really good illustration of some of the things that I think emulation is really good for. So for most of this talk, you're going to see QEMU. You can probably insert some other types of emulation software if you want. And still make the same arguments, but we're going to focus on QEMU today. And I'll talk more about the specifics of QEMU a little later, okay? So hardware is hard. The case for emulation too. Hardware is expensive, right? It's really expensive to design, and it's really expensive to buy, right? So again, I'm using CXL as a bit of a scapegoat today, but probably because it deserves it. CXL-enabled servers cost a bunch of money, right? You don't spend $25 on a Sapphire Rapids-based server, right? You spend an awful lot of money. And they often have a lot of bugs in them. And the bugs might not even be in the CXL part. It might be in something else, right? Or it might not even be in the silicon. It could be in the firmware, and you can't look at the source code for the firmware because it comes from a vendor and you don't necessarily get to play with that, right? Maybe the operating system doesn't have support for the hardware because that's your job. You're the software developer, right? So maybe you're supposed to be writing the driver. So how do you test, the hardware if you don't have a driver yet? If the system breaks, right? If you have a real server and you finally got Intel or AMD to give you one and you have it in your lab and you turn it on and the thing just goes pop and it just doesn't go any further. How do you know what's to blame? Is it the hardware that's bad? Is it the firmware? Is it the software? I often imagine a software developer being somebody who travels the world, either for work or leisure, and they open their laptop in the middle of a coffee shop in Lima. Can they do effective work, right? Ideally, they can. Ideally, they can do that without even a high-speed internet connection. Everything they need could run on their laptop, right? They obviously don't have room in their backpack for a Sapphire Rapids server. These things are pretty big, and I think the other people in the coffee shop would get really pissed off, but barista could probably use it because it will keep everything nice and warm. But anyway, yeah. So what can we do? How do you turn on, say, 10,000 software developers when there's only 2 or 3 working servers with the hardware in them that you want, right? How do we enable a broad ecosystem of development with these kinds of barriers to entry? The case for emulation 3. Hardware is very hard to debug. Look at CXL, for example. Sorry, CXL. I do actually like CXL. And again, this is from personal experience. Not necessarily in my current role, but in other times. I've had CXL-based servers in a lab, and sometimes they take 10, 15 minutes to boot, like literally 10 or 15 minutes before you get a working Linux prompt that you can SSH into and so on and so forth. And you run your test and it doesn't work. And now you have to reboot, right? So a 15-minute lag time on a reboot is pretty horrendous, right? And I've seen people work with that kind of disadvantage. When something goes wrong early in the boot process, how do you may not have even got a console yet. You may not even have any kind of, log or trace that you can look at because things have gone wrong before the UEFI has even started running, or maybe before the Linux kernel has started running, but you don't have access to the UEFI console, right? And I've even seen cases where we've tried to video the screen as its produced output, because it just flashes off at some point, and you want to try and get like the last thing that was on the screen before it's disappeared. And you have to go buy one of those high-speed capture cameras in order to get that last little thing. And then you obviously have to tweak something, recompile it, reboot again and again and again and again. All right. Emulation emulates the hardware using software. So you can literally step through code associated with hardware emulation. So you can basically GDB hardware. That's pretty neat. That's pretty powerful. And that's something that you can do with QEMU and other things. Okay. So the case for emulation 4, this one is not so much a case for it. I mean, realistically, sometimes you actually need real hardware, right? Sometimes performance is important, right? And emulation is typically not going to perform as quickly as real hardware, right? But you'd be surprised how often you don't need that if you're doing software development. If you're writing a management tool for NVMe drives or a fabric manager for CXL, do you really care about performance? Probably not. You care about correctness and some other things, but probably not performance. Obviously, you know, as a real hardware vendor, you actually want to sell something at some point. So ideally, your hardware is going to work. But the reality is, a lot of the time, you can get away with emulation. Okay. So there is a real kind of case for it. And then I just put in this, for some reason, Bohemian Rhapsody spoke to me when I was putting this slide together. So, you know, is it real? Is it a fantasy? Is there escape from reality, right? So perhaps what Freddie was really looking for was an emulation. Okay. So, like I said, I want to focus on QEMU today. I think it's, you know, A, it's very, very powerful, and B, you know, it has so much support right now. It just seems to be moving forward very, very nicely, and it's also open source and permissively licensed, which is obviously very, very useful for everyone. You know, so I'm going to look at emulation in QEMU. Is it real, and do we care? Okay, so I'm sure most of you have used. Has anyone not used QEMU in here? Okay, a few people. Awesome. Okay. Well, if you haven't, hopefully one of the things I'll inspire you to do is at least go take a look at it. So QEMU originated back in 2003. When you kind of Google QEMU and emulation, you kind of get articles in two broad categories. So one thing that QEMU is good at is emulating an instruction set architecture. So let's say, for example, you want to run or develop some ARM code, but you don't have access to an ARM processor or an ARM-based server right now. And in the days before Graviton, that was quite common, that you would actually want to develop for an ARM64, but all you had available to you was Intel machines. Like now we can spin up things, you know, you can rent a Graviton on AWS and get an ARM, or you can go buy something from a few of the vendors out there. But what QEMU lets you do is basically emulate that you're running on a ARM-based virtual machine when you're actually running on x86. And it does something called instruction translation in order to do that, right? It has to take the binary blob that contains ARM64-based instructions and then turn those into something that the host can understand, and that could be running, you know, something like AMD 64 or whatever. And the great thing is QEMU also supports a whole bunch of other ISAs, including RISC-V and a whole bunch of different flavors, and MIPS, and some that you've never even heard of or want to hear of, but they're still there and supported in QEMU. That can also be handy if you realize you have a binary that a customer has given you, and that binary is for some reason compiled to an instruction set architecture that you don't actually have anymore. So QEMU can actually let you run that code. That isn't the kind of emulation I'm going to talk about today, because that's instruction set modeling. The other thing QEMU can do is emulate hardware that is not actually present on the host server. So imagine you have a host server that's full of SCSI drives, but you're a software developer who wants to develop some code for NVMe, for example. What QEMU allows you to do is take some of that block storage and convert it. So inside the virtual machine, inside the emulation, you think you have one or more NVMe drives. And this is the kind of emulation that I want to focus on in this talk, right? So we're going to talk about different ways QEMU can do that, okay? The other interesting thing is that QEMU can allow you to kind of mix and match these different things. So I can build a server that looks nothing like the underlying hardware, nothing like the host. It can have a different instruction set. It can have a completely different set of hardware. And you know, to all intents and purposes, once you're inside that VM, you don't know what reality is anymore. You are totally lost in inception. But you can still take advantage of things like virtualization instructions in the instruction set. So when we talk about things like Zen and KVM, we're talking about leveraging virtualization extensions to the instruction set. And you can actually combine these things. So we've actually had cases where we're running at almost native speeds in terms of CPU instructions per cycle and clock frequencies, but we're presenting very non-real hardware to the software running inside the VM. So that's a very powerful combination. Okay, emulation in QEMU 2. So we're looking at system emulation mode here. So this is not just emulating, you know, a different CPU or running part of a program. This is basically creating a virtual machine in the sense that it has PCIe interfaces and internal buses and maybe even CXL interfaces and networking cards that may or may not actually be there in reality. The rest of, you know, the CPU is either emulated or it's, you know, accelerated by something like KVM. The rest of the system seen by the virtual machine can be a mix of real hardware and emulated hardware. So that's pretty important. I don't have to emulate everything. I can take some of the real hardware in the system. That could include something like a graphics card or an AI accelerator or a network card, and I can give that to the virtual machine. But then on top of that, I can create emulated devices that are not actually real. So the virtual machine may actually start to see a hybrid of real hardware and emulated hardware. And you can even start doing weird tricks where you take a real hardware device, throw a little bit of software on top, and then present that to the VM. So the VM sees a modified version of real hardware. So you can do all kinds of tricks there where you think you're talking to a real NVMe device, and you kind of are, but there's a layer of indirection in there where you can add additional functionality. So you can even get something where some of the hardware is emulated and some of it is not, right? So real hardware can be assigned completely to the VM. And one of the ways we do that, for example, for PCIe devices is via VFIO. And that's a pretty well understood way of taking a real device, in this case a PCIe device, and presenting it to the VM. We can also do this para-virtualization, which is this kind of hybrid mode. Fake hardware can be emulated by QEMU itself or another process running on the host, right? So we can either use QEMU or another process that's somehow connected to QEMU, and I'll talk about that a little bit later. So we're not going to go any further into this whole concept of using real hardware. But if you're interested, you should just Google and follow the links for topics like SRIOV, SIOV, VFIO, and mediated devices. It's a really interesting space, this kind of blended world of real and emulated devices in a system. So what we end up with is a mix of real hardware and fake emulated hardware inside our virtual machine. And QEMU is the software responsible for making that happen. Like I said, and this is really important, once you're in that VM, whether through SSH or whatever other method, you have no way of knowing what's real and what's fake. Okay, you can guess. You could go, well, the performance isn't quite what I think it should be, so maybe this is a fake NVMe drive, or maybe it's just a real NVMe drive having a bad day. I don't really know. That's really an important concept. Obviously, if you can jump out of the VM and look at the hypervisor, you can see what's really going on. But if you're inside that VM and you can't escape it, you don't know what's real and what's fake. You need some kind of totem, right? And this fake hardware is software, right? And I'm going to show you some of this in a minute. We're running lines of code on the host processor to create these virtual devices. So they're just software. And in fact, because QEMU is open source, it's software in source code if you want it, and you can actually step through that code, right? Or you can read the code, or you can modify the code and recompile it. So you can fully control the behavior by editing that source code, okay? So some examples of hardware that can be emulated inside QEMU include storage devices. So if I wanted to create a virtual, I almost did this, I just didn't have time. I wanted to create a virtual machine with like 1,024 NVMe drives, just to show you could do it. And that would work. I could literally pull up a terminal SSH into this machine and go, oh, look, this machine has, 1,024 PCIe slots. And it's each one of those slots is populated with an NVMe drive that has a certain amount of capacity. Let's put a RAID stripe across all 1,000 and spin up FIO and do some IO against it. It would work. It might be slow, but it would work. We can emulate inside a QEMU, we can emulate NVDIMMs, right? And these NVDIMMs, to all intents and purposes, look like real NVDIMMs, right? They have the management interface. You can use user space tools like, NVDIMM control to control them or ask them about their health. And a few years ago in the persistent memory SIG, we did some workshops for persistent memory software development, and we didn't have, or we didn't even want to have access to real NVDIMM servers because they're expensive and you'd have to host them somewhere. And so we used QEMU, and in one of the workshops, I think we had like almost 100 people who on their own laptops were basically running virtual machines that had NVDIMMs on them, or at least they thought that, to all intents and purposes, it seemed like they did. You can emulate things like network interface cards. So you can, think you're talking to an Intel NIC, but the actual NIC in your real system is from a different vendor. Right? And then we have other peripherals, things like roots of trust and security and crypto and et cetera, et cetera. And these are examples that are inside the NVMe source tree, right? So these are part of upstream QEMU. And we'll talk about other types of emulation in a minute. Okay, so I'm going to run through a couple of examples, including some computational storage ones. Who here has a laptop with a KV-capable NVMe drive in it? Do you know what that is? Wow, that's impressive. Who here has a KV-capable NVMe drive anywhere at their disposal, as far as they're aware? 23. Yay! So some people do. I wouldn't be surprised. This is SDC, right? But if you go out into the general world and ask people if they have a KV-capable NVMe drive or SSH access through a VPN to one of those, most people are probably going to say no, and the ones who say yes are probably confused, except for 1 or 2 cases of people who actually do, right? So, NVMe specified the KV command set quite a while ago, but there's not a lot of drives out there, and even if there was, there's not a lot of software out there that can talk to them. So if I want to develop some software that can work with KV drives, either I've got to kind of make it up as I go along, or I need some fake hardware. And then the advantage of the fake hardware is all the stuff I mentioned earlier in the talk. It's cheap. In fact, it's free, right? It's very controllable in terms of it's just lines of C code so I can change it, I can fix it, I can debug it, right? The performance might not be as good as a real KV NVMe drive, but at some level, how much do I care about that? All right. So let's take a look at life inside a VM. So here's a VM that I span up earlier. And if you do a LSPCI inside this particular VM, you get a list, as you would on a real server, of all the PCIe devices in this system. And what's interesting is one of these devices is a non-volatile memory controller device, which is an NVMe device. And it's by a vendor called Red Hat. And the funny thing is, last time I checked, Red Hat did not make real NVMe SSDs. Okay, so this is my totem. This tells me that this is not a real system. And in fact, this system is pretty much, every single device on that list is not a real NVMe device. Okay. Now, the virtual machine does not know this. The virtual machine is not running a single line of code that wouldn't work on a real system. It's running Linux. It's actually running Ubuntu 22.04. All the tools still work. But these are not real devices. So what's going on? Okay, of course, this is an emulated NVMe device. The code running inside the virtual machine has no way of knowing if that particular NVMe SSD is real or not, except the Red Hat kind of gave it away. I think the second point is super important. The code running inside the VM is identical to the code that would talk to a real NVMe SSD. This is where the real power to the software developer comes in. Basically, if you want to develop code for an NVMe SSD that has new features, and you do it on an emulated device, then assuming the emulated device is an accurate and correct reflection of the standard or the proprietary feature, if you're adding a proprietary feature, that same code your developers have developed should work on the real hardware, right? So that could include things like the kernel driver. If you want to develop the kernel driver for something, if you want to write a user space tool, this will let you have that code ready to go when your hardware comes. It also lets you explore what would happen if you did add certain new features to NVMe, for example. So we can add or remove features to that particular Red Hat NVMe SSD by changing the source code of QEMU, right? So we're not changing the code inside the virtual machine. That's still just running Ubuntu 22.04. We're changing the source code of QEMU, this emulation / hypervisor software, which is free and open source and on GitHub. And you can take it and you can change it and you can fork it and you can have an internal proprietary fork and you can give it back to the community later. So that means you can explore new NVMe features. And like I said, they can either be standards-based or they could be vendor-specific before hardware becomes available. And I think two of the examples that are pretty relevant to SDC this year are things like key value and FTP, flexible data placement, of which there's like 8,000 talks today or tomorrow. So assuming that point 2 is true, that means software developers can write code for new hardware without needing new hardware. So that's pretty cool, because new hardware is hard, expensive, blah, blah, blah. Okay. And like I said, this code is not like hidden, buried away, or secret, or like locked in a safe, or like nobody's allowed to look at it or touch it. It's on GitHub. It has a huge development community. There's mailing lists. The actual maintenance is done through mailing lists, I think. Somebody correct me if I'm wrong. GitHub is just a mere reflection of the latest state. They do releases pretty regularly. And it's licensed very permissively. You can take it and fork it and bring it inside your company behind a firewall if you want and make changes that are not public domain. And you can give those changes back if you want or whatnot. So anyway, if you go on GitHub, like you can do it right now. If you go down through into the hardware subfolder at the top level, you'll find a folder called NVMe. And in there, there's a bunch of files. Right, I'm going to actually go over here. And there they are. You got a config file, you got a bunch of .c files, which, as you might imagine, are C source code. You've got some header files, you've got a Meson build file, you've got this thing called trace events, which is for tracing, which I'll maybe talk about. I don't have a slide on that, but tracing is super cool. And that source code implements NVMe, right? That source code is an emulation of an NVMe drive with a bunch of different features in it. And when you compile QEMU, you compile this code as part of that. And then when you instantiate QEMU, if you set the options correctly, you will get an NVMe drive with a certain number of features. If you want that NVMe drive to be exabytes in size, you can do that. Now, don't try and fill it, because you're not going to have enough space to do that. But if you want to, you can. You can also have that NVMe drive do all kinds of crazy, weird things, but the one that's upstream is pretty good in terms of conforming to the standard and the functionality within there. Okay. So let's say I want to add KV capability to an NVMe SSD. There's two ways of doing it. There's the hard way and the easy way. So the hard way is go build a real SSD and go through all the pain that's associated with that. And then allocate a bunch of overcommitted firmware engineers to the project and ignore the howls of process from sales, marketing, management, etc., because those firmware engineers should actually be working on firmware that's generating revenue for your customers, and KV is just something else that you're working on. You write firmware that implements the KV command set on that SSD. You debug the firmware, and then you validate that you have this KV correct, and you then try and sell that to your customers. Ideally, you have a customer up front. That's going to help with item number 2. But if you don't, you have a problem. And firmware engineers are never just lying around doing nothing. Anyone who works at a company that has firmware engineers who aren't over-allocated, please tell me, because I've never seen that to be the case. So that's the hard way of doing it. The easy way is basically clone QEMU, change directory into the QEMU folder, check out a new branch, make about 379 lines of code change. I'll show you where I got that number from in a minute. Commit that change back into there, build QEMU, spin up a VM using this new version of QEMU, and assuming you did everything correctly, when you look at the NVMe drive in your system, it has support for the KV command set. And you can actually do loads and stores and check for the existence of a key, et cetera, et cetera, et cetera. And then if you really want to, you can upstream that code. As in, you can give it to the upstream version of QEMU. And the interesting thing is that Samsung have actually already done everything from 1 to 8. So thank you, Samsung, right? So the only thing they haven't done yet is upstream. So basically, if you want a KV NVMe SSD, you don't even have to write the code, it's already there. And in fact, the code exists on Samsung's fork of QEMU. So anyone who's interested can go and do that. I think the commit associated with adding the key value commands is 379 lines of code, which is where the 379 came from on the previous slide. So rather than building a new chip or writing a bunch of new firmware and validating it, I just needed, and I didn't even need to do this myself, I just went to somebody else's repo, but I needed to make 379 pretty much additions to that NVMe model, and I've got a key value namespace capable SSD, right, ready to go. If I wanted to add some non-standard key value commands, let's say I want to be able to store multiple key values at the same time, I could add that by adding a few lines of code to this model, right? If I wanted to experiment with some computation on some of my key values, I could add some code to do that too, right? So it becomes very easy to start playing around with new hardware. Okay, this is another one that I really like. So this combination of NVMe and CXL is something a few of us have been talking about for a while. So here's an emulation of taking something that doesn't exist at all yet, though multiple vendors say they're working on it, a CXL switch, and putting a couple of different devices below it. So this is something that we've been very keen at looking at for a few different reasons. So I have a processor, from a vendor. And the great thing is with QEMU, this could be a RISC-V 64 instruction set. I don't have to be Intel or AMD or Huawei here. I can build my own SoC with my own emulated hardware running the instruction set that I want. Right? It has some DRAM hanging off it. I want a CXL switch. And then below the switch, I would like some CXL Type 3 memory expansion devices. And I want some NVMe SSDs. For some reason, when I go to hardware vendors today and ask for this, they tell me I can't have it. And that really annoys me. Right? One of the reasons we want this is because we're looking at things like memory expansion. Can we use NVMe SSDs and CXL to increase the memory footprint, albeit at latency costs, to a system? We also have been, I've worked personally a lot on peer-to-peer DMAs, so DMAing data from NVMe drives into different I/O devices. We'd like to be able to do the same here, where I can basically issue an NVMe command to this device, but it actually puts the data here. That's really good for prefetching, which certain applications love, right? So we could use that for prefetching or for swap or for page cache acceleration. But in order to make that all work, you have to write a bunch of software. But if you don't have the hardware, how do you test that software, right? So my team, they want this hardware. They can't have it in reality. But if we can emulate it, then we can do a bunch of work, a bunch of research, maybe publish some things, maybe open source some code. And when the hardware does become available, we're ready to run with it, right? So what do we need? Can we build it today? Well, we can, as long as we're willing to move to the world of emulation. So I'm not going to go into all the specifics, but basically, if you run a certain branch of QEMU with all these particular options and with a particular kernel that isn't actually upstream yet, but it's Jonathan Cameron's branch, you actually get the hardware that I showed you on the previous slide. All right, so let's just repeat that. If I take a certain version of QEMU, which is not the upstream version, but it's a branch, and I compile that, and then call it, invoke it with these options, and then make sure that a certain non-upstream version of the Linux kernel is running on the VM inside that version of QEMU, I get, or my team gets, or you get, or the people you work with get this hardware, okay? Which isn't going to exist in the real world, I'd estimate, for another 2 to 3 years, okay? Okay, one other quick example. A bunch of people are looking at taking a whole bunch of servers and connecting them to a top-of-rack memory area network, as certain people like to call it. So I have a bunch of processors. They have a certain amount of direct attached memory. The rest of their memory comes from a CXL fabric. If I ask the hardware vendors if I can have that in my lab today, they laugh at me. But Memverge just the other day basically showed how you can emulate it using QEMU. Now, I think right now it only supports 2 hosts that are sharing some CXL memory. But that's certainly better than what I can do with real hardware. So again, I can emulate this. I'm not going to go into the specifics, but if anyone's interested, they did a blog post on it. I think it was only like last week or the week before. Okay. So I'm going to kind of jump into a little bit more of a computational storage example here. So everything until now has talked about emulating by changing the QEMU source code itself, right? So go to GitHub, check out or clone the QEMU that's there, make some edits, you get some new hardware. There is another way of doing this, which is where we have the emulation code running outside of QEMU. I'm going to look at an example, and Jim Harris is here, newly moved to Samsung, and he's one of the SPDK maintainers, so SPDK actually features a little bit here. So up until now, we've looked at emulations that are based on software that resides in the QEMU Git tree. This is great, but not all the devices that we ever want to emulate deserve to go upstream, in which case you have to maintain your fork, and that can be very painful because you need to keep it up to date. But there are other really good, there's really good code out there that isn't QEMU, right? SPDK is a really good example. SPDK is a great user space storage stack. It can do lots of weird and wonderful things. And maybe I want to leverage that and QEMU, right? So what we are able to do is to have two different processes. One of them is QEMU, and the other is something else, right? They need a way to talk to each other, though. Otherwise, how does QEMU use that as a hardware emulation? And a team at Nutanix actually came up with a solution to that, at least for PCIe devices. So we'll talk about that on the next slide. So, if you want two processes to talk to each other, there's a few different ways of doing it. One of the classic ways is sockets. So a team at Nutanix have proposed something called VFIO-user. This is a mechanism that allows PCIe devices, and right now it's only PCIe. It could be extended pretty easily for CXL. So that is something that we're looking at, that allows PCIe devices to be emulated in a separate process to QEMU. So you spin up QEMU, run it as a process on your operating system. You spin up another process, could be SPDK, could be something else. And then this thing called VFIO-user has two components. One is a socket, so a kind of a client kind of model. And then there's also a protocol, so both sides know what language they should be talking in order to communicate with each other. SPDK has already been updated. I think that's upstream, right? Yeah, Jim's nodding his head. So SPDK has been updated to support being an NVMe emulated device. And so the way that it works is our hypervisor is the client. So it's a little bit weird because I would have thought it would be the server, but there's a reason why. It's the client. And then you have this other process that could be just some code you've written yourself. Could be SPDK, could be Steven's weekend project, could be whatever. But assuming you do everything right and you use the VFIO-user library and everything works well, what happens is this hypervisor will expose a new type of PCIe device to the VM or VMs inside it. And, you can do anything you like with that process, including building computational storage drives. Okay? So if we replace Cloud Hypervisor, which is a Nutanix hypervisor, with QEMU, we kind of have this model of PCIe device emulation. So what we've done is we've modified SPDK to start supporting some of the new upcoming command sets, right? So TP4091 is computational programs. TP4131 is subsystem local memory. And these pertain to computational storage. And what we can do then is use QEMU and VFIO-user to expose this as an NVMe computational storage drive. So now inside the virtual machines inside QEMU, you see this PCIe device that doesn't just support LBAs and FTP and KV, but also supports subsystem local memory command set and 4091 command set and maybe some other proprietary vendor-specific command sets that we're experimenting with. And again, as far as the VM knows, that's a real device. It's as if someone had actually gone and built some silicon and attached some NAND and done all that. Oh. So the question is, what software goes inside the VM? Now, if I have a computational storage drive that supports 4091, I need some software on the host that can talk to it, right? And so that's, what the software developers are developing. And so, there's multiple parts to this. Some of them are being done by my team in Huawei. Some of them are being done by Samsung. Some of them are being done by WD. Some of them are being done by Solidigm. But via a combination of the Linux kernel, right, especially things like IOU ring with command pass-through, and things like XNVMe, which is a user space library for NVMe commands and command management, and SNIA's Computational Storage API, right, which Samsung and others have been working on, we can tie our emulated computational storage drive to real applications like Spark and Mindspore and whatever, right? And like I said, that software that we've developed will just work on real devices, right? So this is developing code that will work just as well on real hardware when it becomes available as it does on emulated. And with the emulated, we can start making pretty accurate assessments of what are the performance gains, what are the challenges, but all in an environment that I can literally do on my laptop from my coffee shop in Lima without requiring any fancy hardware. And I have full visibility because I can GDB, step through everything, including the hardware. And, I don't have to worry about firmware blobs from a vendor. I have full visibility, full control. And I can explore what happens if I modify some of these commands or add new commands. And I think that's a pretty cool place to be. So a little bit of a kind of, this is, where we're going, or this is the power of emulation. My team is, very actively working on what happens when you start having all of these pieces, right? These are all just building blocks, but now you have them, what can you do with it? So the things I'd like people to take away is that real hardware is hard, right? Building real NVMe drives with new command sets, that's a lot of challenges are there. And most of the time, your software developers, or not even your software developers, but the community of software developers that are out there, don't even need it. QEMU is not, the only thing out there, but it is on a roll. I've been really impressed with how much QEMU has evolved in the last 3 or 4 years, where I've been working with it. It's a very successful hypervisor and also a really good system emulator. Get to know it, for those of you who haven't already. Emulation can be done inside the QEMU source tree, and this can be ISA emulation and or hardware device emulation. Emulation of PCIe devices, at the least, can be done outside of QEMU via libvfio-user. And like I said, extending that to CXL shouldn't be super complicated. The advantage of that is, of course, you can keep the QEMU source tree clean, and also you can leverage excellent code that lives outside of QEMU. All of these parts are coming together to allow us to do CSD or CSP or CSA emulation. And hopefully that's going to enable the software developers to start writing the code that will run in Linux or in user space above Linux to tie these devices to applications, which I think will just drive a market and help us understand where can we deploy computational storage and where can't we. And just because Shannon's in the room, I'm going to also finish with this. I didn't mention some other interesting hardware that's out there, but there's been a bunch of work in SNIA around SDXI, which is a data movement kind of protocol / standard. And another interesting idea is, can we talked about NVMe and CXL a lot today. Can we emulate SDXI, right? Which is another thing then that we could write some software on top of and go, okay, where is SDXI useful and where isn't it from a, where is it easy to use, where is it hard to use, what software has to be written, what doesn't. So again, another example where emulation can be very powerful because we don't have line of sight on a real processor with an SDXI-based data mover in it yet, right? So a chance to, again, get ahead of the curve. That's all I've got for today. Thanks for listening. And yeah, questions? Yes, Gary. Yep, so the question, just repeating for the video recording, was in the example where I showed CXL switches and CXL devices, an emulation of type 3, can we also be emulating type 2? The answer to that is yes. The upstream version of QEMU right now only has support for type 3 device emulation, and there's a bunch of work going on, like right at the cutting edge of upstream QEMU to kind of bring that to a certain level of maturity. For type 2 devices, which are more like accelerators, I think that's where something like VFIO-user extended for CXL support could be very interesting, because if you do a bespoke accelerator that accelerates a certain application, there isn't necessarily enough of a user base to justify that code in upstream QEMU. You might have a hard job convincing the maintainers to take that code, because they'll be like, well, this is a one-off accelerator. How do I know you're going to be around in 2 years to maintain this, blah, blah, blah. So having those types of things maybe out of tree could be very interesting, right? So I think there's two ways to play that. If you had an accelerator you're thinking of developing, and you wanted to, enable software developers, you could either create a fork of QEMU and add the code there, but the problem is your fork won't stay up to date with QEMU unless you pay someone to kind of keep it up to date, right? And or the other option is to go down the path of let's update VFIO-user so it supports CXL as well as PCIe, and then we can have these kind of accelerators as their own repos, whether that's SPDK or something else. So I think both are interesting. CXL? I don't think it's a big thing. I'd say it's a medium thing. So we have talked to Nutanix team a little about it. There's a lot of similarities. Obviously type 1, CXL.io is very like PCIe, so that one's kind of pretty straightforward. We don't think there's a huge amount of work on .cache and .mem, but I'll be honest, I haven't really sat down and created like a really accurate assessment of how much work that would be. But it's something that's on our radar, and if it's on Lanel's as well, Gary, we could definitely see if there's enough interest from enough people to make it worth taking that on. The other thing I would say right now is VFIO-user doesn't really have an official home as a standard. It's like this Nutanix thing that has kind of lived its own little life. Maybe there's a better place for it to live, maybe even SNIA, right, where it can have a more official home. And then we can work on it together in a more formal fashion. Right? So something also to be discussed. You had a question, and then I'll come over to you, Paul. Yeah. So the question is, did we have to modify VFIO-user, the protocol spec, or libvfio-user, the Nutanix code that implements that spec? And the answer is no. For this particular work, the SPDK work, we had to make no changes. Now, we had to make changes to SPDK to support the new command sets, but no changes were required to libvfio-user. That's a good question. Paul? I figured it out. Okay. If there's no other questions, we will call it there. Oh.
What is your relationship between SPDK and VFIO?
What's that? Sorry?
What's the relationship between SPDK?
Okay. So the question is, what's the relationship between SPDK and libvfio-user? So what we're doing here is we're running a virtual machine manager that runs the VM, right? So that's the first part, QEMU. Next, what we need is some kind of C code that emulates the NVMe device, right? That part is SPDK. But what the third part is you need some way of the two things I've just mentioned to talk to each other in a way that is aligned to some kind of standard so that when this one says, I would like to do X, the other one knows how to reply. And that's what VFIO-user and libvfio-user do. So libvfio-user and VFIO-user are basically a way of saying, I have two different processes, and I'd like them to basically talk like a PCIe master and a PCIe slave. And that's what that does. Yeah. Yes? So libvfio-user and the VFIO-user protocol spec only support PCIe today. Gary Grinder asked the question about extending that to CXL, and the answer is yes. I think it's a moderate amount of work to extend VFIO-user to CXL, but I haven't done all the work on what it would be required there. But we feel like it's not easy, but it's not super hard. It's more like moderate amount of work. And then we could emulate CXL devices as well as PCIe devices. Okay, I think I'm out of time, but thank you.